Yeah, let's start.
Okay. Okay. So good evening, everyone. Welcome to IGC. Uh, so this session is just a moment. Okay. So let me just see the YouTube part. Okay. So this session is a demo session for the crash course batch. So what we'll be doing is I'll just explain you a topic in aerodynamics, a very interesting topic, and we will understand that in brief. Okay, we will really not go into the depth of the derivation and all. The idea is just to understand understand the concept, and then we'll try to solve some problems. Okay, so if you guys have any doubts in between, please try to you can interrupt me, you can stop me, and you can ask your doubts. Okay, you can put them down in the comment section. Okay, so yeah, before starting, just a quick introduction. My name is Sanjay. I teach aerodynamics here at IGC, and I am a graduate of IISc from in aerospace engineering, and my specialization is aerodynamics. So let's get started now. So generally in aerodynamics, the entire syllabus, what we do is we break them down into few modules. So we start from governing equations, right? So what is aerodynamics? Aerodynamics is basically the study of flow past bodies, right? So we are studying external flow past bodies. Now, what kind of bodies do we deal with? We deal with bodies which are very slender, very thin, and which produce aerodynamic forces, right? Aerodynamically designed bodies. So we are talking about bodies like something of this shape, right? Do you all know what is this shape? Yeah, you definitely would have heard about, you would have seen this. What is this shape called as? Yes, guys. Those who are watching can comment or speak.
Airfoils.
Sorry?
Airfoil.
Airfoil. Yeah, very good, right? This is an airfoil. So this is basically the cross section of the wing, right? So we are mostly going to discuss flow over airfoils, right? So we will aerodynamically analyze this shape. Why is it given such a shape, and what are the aerodynamic characteristics as such? What lift is generated by this shape, right? What is the drag, right? Various other things. So then we will deal with different types of airfoils. What is the nomenclature? What are the basics of wings and all? Then we will see some theories in aerodynamics, which is potential flow theory, thin airfoil theory, and finite wing theory. Now these theories form the pillar of aerodynamics. Okay, so entire theoretical aerodynamics is situated on these theories. So these theories will basically try to give you closed form expressions or analytical solution for flow over such bodies, right? So now the thing is, when we study these theories, we always begin with some assumptions, right? What is the prime assumption, or what is the main assumption behind these theories? Is that we will mostly be dealing with incompressible flows. Okay, we will mostly be dealing with incompressible flows. So this is one of our main assumption, that the flow field is incompressible. When I say the flow field is incompressible, what do I mean? I mean that the density is constant, right? We are not really considering any changes in the density. So we basically say that we are going to satisfy the governing equation for incompressible flow, which is uh, del dot v is equal to 0, right? That is a continuity equation for an incompressible flow. So the main assumption is that the flow field is incompressible, and the entire theory is built on that, right? The potential flow theory and thin airfoil and finite wing theory basically is again laid upon potential flow theory. So all the assumptions of potential flow theory is going to be equally applicable on thin airfoil and finite wing theory. Okay, so this incompressibility is our main assumption, right? Now this is just a continuity equation. We also have other equations like momentum and energy equation, which we additionally satisfy. Okay, where again we consider density is constant. Okay, now now yeah, now what happens is, let me ask you, what is the typical Mach number at which our commercial aircrafts operate? Like the conventional aircrafts that you see flying today. Do you have any idea what is the typical Mach number at which they operate? Yeah, 0.3. Is it really 0.3? Is it that low Mach number? Anyone? 0.8, right? So yeah, so you are right. So the typical Mach number at which our commercial aircraft today operate is from 0.8 to 0.9, right? So what kind of Mach number is this? Is this, do you think this is really, so this is of course a subsonic Mach number. So any Mach number that is less than 1 is subsonic. But do you think the flow when it is in Mach 0.8 to 0.9, is it really incompressible? Yeah. Is it an incompressible flow? No, right? The flow is not incompressible. So we then, if we talk about these theories, which is telling you about the aerodynamic forces and moments, and if the flow is of Mach number 0.8 to 0.9, which is not incompressible, then we are going wrong, right? Because our assumption is the flow field is incompressible. So the entire low speed aerodynamics, when you study that for an incompressible flow. But then the Mach number at which our aircrafts are operating is compressible, right? They are highly compressible because 0.8 to 0.9 is a compressible Mach number. So what is that limit? Does anyone know? What is the limit of the Mach number above which I can say that the flow field cannot be considered as incompressible anymore? What is that limit? Anyone knows? What is that limit of Mach number above which you cannot consider a flow to be incompressible? Any idea? Not one. No, we know from 0.8 to 0.9 itself, it is not incompressible, right? So obviously the Mach number is below that. So which is that Mach number above which? Yes, very good. So Kanishka has answered. It is 0.3, right? So generally, this is not really like something which is accurate. It is a rule of thumb. Okay. So by rule of thumb, we say any Mach number, the free stream Mach number, if it is greater than 0.3, we cannot consider the flow field to be incompressible, right? You have to account for the compressibility effects, right? So all our theories which we have studied when we say the flow field is incompressible has become invalid, right? So what do you do? So how do you treat that, right? For that, we are going to learn this particular concept called as how to deal with a compressible flow, and it is subsonic in nature. Okay, so we are dealing with subsonic compressible flows, right? So there are some interesting features that happens when the flow field becomes compressible. Okay, and these features are very crucial to the aerodynamics, to the performance, to the structures of the aircraft, right? So it is important to understand these concepts, right? So we will get started with this. Okay, so these are the governing equations for a general compressible flow, right? You know what are the governing equations? We know we have three important governing equations: continuity equation, the momentum equation, and the energy equation, right? So you see the first one is a continuity equation, which talks about the mass conservation. So on the left hand side you see the integral forms, and the right hand side you see the differential form of the same equation, right? So we have the mass conservation, we have the momentum conservation, right? Or we can say these are the Navier-Stokes equations, right? These are the Navier-Stokes equation, and here you see you have the energy equation, right? Now, when we deal with incompressible flows, it so happens that due to the kind of unknowns that we have in the governing equation, we don't need the energy equation, right? For incompressible flow, we can do well with continuity and momentum. But when you come to compressible flows, right, when you talk about compressible flows, because of one more parameter, namely density, right, density starts to vary. So density has to be accounted for. You need one more additional equation, that is the energy equation, right? So you have to deal with energy equation additionally for a compressible flow, right? So now your equations, how many equations do we have? We have three momentum equation. Because it's a vector equation, you have three components. You have one energy equation, you have one continuity equation. So you have total five equations to deal with. Additionally, on top of this, you also get one more equation, which is the equation of state, right? We cannot forget the ideal gas law, P is equal to rho RT. So this also becomes one more equation with five. So totally you have to deal with six equations. Okay. So these equations will govern the compressible flow. Okay. Now, so if I want to deal with the six equation, it is very complex, right? Like, how do I solve these equations to obtain the flow field? So what do I do? Let me try to make these six equations compact, and let me see if I'm able to reduce them to some single equation or something like that. Okay. So for that, let's see a comparison between incompressible flow and a compressible flow. Okay. So you can see here the incompressible flow and compressible flow. What are the main differences? Let's consider a 2D flow, a steady and a rotational flow. So when I say the flow is irrotational, I'm saying the curl of velocity vector is zero, right? Del cross V is zero, right? So when the curl of velocity vector goes to zero, or when the vorticity goes to zero, I can express the velocity vector as the gradient of a potential function phi, right? So I can say V is equal to grad phi, right? From the rotationality aspect. Now the same thing is also applicable for a compressible flow, right? It is also applicable for a compressible flow, because we are only saying the flow field is irrotational. We are not saying anything about incompressibility or compressibility. So the phi is equally valid for both compressible and incompressible flow. Okay. Now, if I can write like this, I can write my velocity components as a derivative, partial derivative of phi, right? U is dou phi by dou x, V is dou v by, sorry, this is phi, dou phi by dou y, right? Same I can write for compressible flow also, right? It is valid. Okay. Now, when I say the flow field is incompressible, on top of this irrotationality condition, when I impose incompressibility condition, I can say that I have to deal with this equation, which is called as Laplace equation. Okay. It is a Laplace equation, right? Because on top of this, I am also satisfying del dot V is equal to zero, which is a continuity equation for an incompressible flow. So when I merge these two, equations, I get the Laplace equation. Okay. Okay, so this is a very good, very important Laplace equation, which is, you can see it is a second order PDE. It's a linear PDE. It is very helpful because it is only from the Laplace equation the entire potential flow theory is developed. Okay. Now, the corresponding Laplace equation for a compressible flow is not like this. It is not very straightforward. So if you see that, this equation is something like this. Okay. We are not going into the derivation of this. This is derived from continuity equation, momentum, and energy equation for a compressible flow. But I just want to give you a flavor of what kind of equation is this. Okay. So you can see this is a velocity potential equation. We can't call it a Laplace equation because there are terms involving mixed derivatives. There are nonlinear terms, right? So it is not a Laplace equation. It is a velocity potential equation. So for an incompressible flow, when I have Laplace equation, for a compressible flow at the same time, I'm having a different equation, but which is again in terms of phi, which is called as velocity potential equation. Okay. Now, what is the use of this? So this is a linear PDE. Laplace equation is a linear second order PDE, but the velocity potential equation is a non-linear PDE. right? You see the non-linear terms, dou phi by dou x the whole square, right? You see the multiplication terms, which is non-linear. So obviously we know we cannot deal with a non-linear equation very straightforward manner, right? So what do you do then? If we cannot deal with a non-linear PDE easily, what do? We try to linearize it. So we linearize it, right? Now, when you linearize it, again, the linearization is true only when you put some assumptions, right? You have to state some assumptions, and only based on that assumptions, you will be linearizing it. So when I linearize this equation, I get a very simple equation, something like this: 1 minus m infinity square dou square phi by dou x square plus dou square phi by dou y square is equal to 0. Okay, which looks similar to sorry, which looks similar to Laplace equation, but it is not similar. Okay, now when I linearize this, what are the assumption? The assumption is that this is valid only for thin bodies. It is valid only for a slender body, okay, very thin body, which is at a very small angle of attacks. Okay, this is valid for thin bodies, which is at very small angle of attacks. And this is valid only for subsonic and supersonic Mach numbers. So this is not really valid in transonic region, right? What is the transonic region? Transonic is from Mach 0.8 to 1.2. So this is not valid in that. This is how the linearization is done. Okay. So after linearizing, you get this equation. Okay. Now what do we do with this equation? So people were wondering about this long time back, and the problem was, see, when how do you get aerodynamic data? So if I want to test a flight or an aircraft for aerodynamics, I create a model, I place it in the wind tunnel, I do a wind tunnel test, I get the lift distribution, drag, pressure distribution, whatever, right? So all the aerodynamic data is obtained from the wind tunnel experiments. Now, the wind tunnel is generally a low speed tunnel where the flow field is fairly incompressible, right? So we are dealing with an incompressible flow. But in reality, the flow field is compressible. So what do you do then? So is that all the data that you have collected for an incompressible flow wrong, right? Is that so? Or how do I treat that? So people thought about it, and two scientists called as Prandtl and Glovert, they came up with some compressibility corrections, which is known as Prandtl-Glovert's compressibility correction. So what this correction tries to do is, this correction tries to take the incompressible flow data, it tries to correct it for compressible flow. Okay, so we have a factor here. That factor will try to make incompressible flow aerodynamic data into compressible flow aerodynamic data. Okay, so we will see what exactly this correction does. So you take an aerofoil here, okay, which is placed in a free stream. So yeah, we saw this equation just now, the linearized velocity potential equation, where beta is 1 minus m square. Okay, so what do you do is, now you can transform the variable. Now this aerofoil is in xy plane where there is a compressible flow. I'm going to transform the variable. So I transform the variable from xy plane to zeta eta plane. Okay, I transform the variable from xy plane to zeta eta plane such that zeta is equal to x and eta is equal to beta y. So this is the transformation that we define. Okay, so when I transform this, the velocity potential also gets transformed because that is a function of x and y. So that also gets transformed. So this, the potential function that you get after the transformation, is an equivalent incompressible potential function that takes into account the compressibility effects. Which means if I make another coordinate, another plane, which is a zeta eta plane, okay, and I have the same aerofoil, okay, now here if I see, the kind of flow which is in zeta eta plane is going to be an incompressible flow. But in reality, the flow in xy plane is a compressible flow. So I'm transforming this compressible flow to incompressible flow, but in different coordinates, right? So basically I am saying compressible flow in xy plane is converted to incompressible flow in transformed plane. Okay, when I do this transformation, I get this equation, which is exactly the Laplace equation, right? Which is exactly the Laplace equation, right? It looks like the Laplace equation, which is incompressible form of Laplace equation, but only thing is it is in the zeta eta plane, right? Which means if I solve this Laplace equation and I get my pressure distribution, I get my lift distribution, right? Then all of that is only changing by a factor beta. What is beta? Beta is root 1 minus m infinity square, right? All of this is only changing by a factor beta. So you can see Prandtl and Glover, they gave a rule saying that if I know my incompressible coefficients, Cp is the pressure coefficient. If I know my incompressible coefficient, and if I just divide that by this factor beta, I get the equivalent compressible coefficient. Okay. So if I want to find Cp in a compressible flow, I need to know what is my Cp in an incompressible flow first. I need to know my free stream Mach number. I plug it in here, I get the compressible form of Cp. Same thing goes for Cl and Cm, because Cl and Cm are derived from Cp, right? You integrate pressure distribution, you get lift and moment distributions. Okay. So Prandtl-Glover rule is just telling you that the incompressible coefficients can be transformed into compressible coefficients by the by introducing this factor beta, right? So this was a correction that was done to account for compressibility effects, right? So now we will see, once this is done, when you move closer to Mach 0.7, 0.8, what really happens? Something interesting happens on airfoil. Okay, so let's see that. So next slide, I'm going to show you something. So please guess what is this, okay? And you can comment. Yeah, so you see here, yeah, what do you think this is? Have you seen this? If you can tell me what phenomena is this, and what is this aircraft? It is a very popular phenomena. What is happening here? Anyone? Expansion. Okay. What expansion is that? Can you be more clear, Vamshi? Very good, Akash. So, yeah, Shriram, sonic boom, right, right. So, this is nothing but basically it is the sound barrier, right? So, and can someone tell me what is this aircraft which first broke the sound barrier? What is this aircraft? Yeah. Okay. So it is Bell X1. Okay, that's the first aircraft that broke the sound barrier. Now, what is a sound barrier? Does this concept exist today? No. We know it is a myth, right? Today it is a myth. Back then, before World War II, around 1930s, this was considered a fact, right? Now, what is a sound barrier? So, people saw when the aircraft is close to sonic Mach number, that is, when you are flying close to Mach 1, okay, you are not reached 1, but when you are flying close to Mach 1, almost when your Mach number is equal to 1, people saw such vapor clouds forming on the aircraft. Okay, such vapor clouds forming on the aircraft. Now they were not able to understand what is this vapor cloud and what is this strange phenomena that is happening, right, out of nowhere. This does not happen when you are at low Mach numbers, but slowly when you go at high Mach numbers close to 1, you see such vapor clouds, right? So what is this? So and people observed that if you try to plot the drag versus Mach number, right? CD versus Mach number. It was observed that as you increase the Mach number, the drag coefficient initially is constant. After some time, after some particular Mach number, the drag coefficient rises. Okay, it starts to rise. It starts to rise, and exactly at Mach is equal to 1. This drag coefficient is at its peak. Okay, the drag coefficient is at its peak. It is at its peak means the drag becomes so high that at that time, during those days, I'm talking about times before World War II. Uh, so people thought we don't have powerful engines which can counteract such drag, right? It is not possible to fly near that. So then, this what did this mean? This meant that you cannot cross the sonic Mach number. That is why it is named a sonic barrier. But today we know this is not true. We have crossed sonic, we have crossed supersonic, we are in hypersonic flights today, right? So it is not true. So what happens? So then later on through experiments we found that the drag actually reduces once you cross the Mach 1. So it is only in the transonic regime that you get such a high drag. But if you cross the transonic regime, then you have considerably lower drag, right? Which can be managed through the engines that we have presently. Okay. So we will see such phenomena. What exactly is this phenomena? Okay. So this phenomena is known as drag divergence. Okay, where suddenly the drag increases is known as drag divergence. So before studying what is drag divergence and before going into the uh, equations and all, we will study another important concept, okay, which is known as critical Mach number. Okay, so critical Mach number is something, it's a very popular concept that comes in a transonic flow. So let's see what is this critical Mach number. Okay, so consider a aerofoil here. Let's say it is placed in a free stream Mach number of 0.3. I'm sorry. So consider it is placed in a free stream Mach number of 0.3. You take a point on the aerofoil. The flow is going to expand. So the local Mach number at point A is 0.435. Right. So the Mach number will increase. Now slowly I am increasing the free stream Mach number. Okay. Slowly I'm increasing the free stream Mach number. As I increase the free stream Mach number, I observe that the local Mach number at point A is also increasing, right? Because the flow is accelerating, so the local Mach number at point A is also increasing. If I further increase my Mach number, it can happen that at a particular value of free stream Mach number, the local Mach number at point A becomes equal to 1, which means the flow has become sonic at a particular Mach number, right? That free stream Mach number at which the local Mach number on the aerofoil becomes equal to 1 is known as critical Mach number. Okay, it is denoted by MCR in the subscript. Okay, so what is critical Mach number? It is that free stream Mach number at which you first observe a sonic flow on the aerofoil. So first, when you encounter a Mach 1 flow, that free stream Mach number is your critical Mach number. Okay. So generally, for our conventional aircrafts, critical Mach number ranges from 0.7 to 0.8 to 0.85. Right. It's around that region. So this is the critical Mach number. Now, what happens if I further increase the Mach number above critical Mach number? If I do that, what do I see? I see there is a supersonic pocket on the aerofoil. So there's a region on the aerofoil where the flow field becomes supersonic, where Mach number is greater than 1. And the supersonic pocket is covered or it is encompassed by a sonic line. Sonic line is where m is equal to 1. Okay, so I have a supersonic pocket and a line, sonic line. Okay, now the supersonic pocket is something very advantageous for an aerofoil, because supersonic flow means you are now getting more lift, plus there is no shock here, right? Because we know generally in a supersonic flow you have shocks, but there are no shocks here. The supersonic pocket is smoothly ending on the airfoil, so you have more lift without much drag. Okay, so this is very advantageous for us. Okay, so if I go above critical Mach number, I'm still getting a favorable condition, but that is only up to a certain extent. It is not that I keep on increasing the critical Mach number, I'll keep on getting this pocket. Okay, so what is critical Mach number? It is a free stream Mach number at which sonic flow is achieved. And how do we estimate this? How do we estimate the critical Mach number for an aerofoil? So what we do is actually we write the expression for CP. So you write the pressure distribution over the aerofoil when your aerofoil is at critical Mach number. You can derive this easily from the definition of CP. Okay, and you try to plot this. When you plot it, you will see this curve, right? You will see this curve when you plot it, the curve that I have highlighted just now, right? And we have one more solution, which is from the Prandtl-Glover compressibility law. That is, Cp for compressible is Cp naught by root 1 minus m infinity square, right? So we have to plot this also. So when you plot this, you get this curve. You see that both the curves will intersect at a location that will give you the critical Mach. Okay, so this is how we find the critical Mach number. Okay, so is this clear, everyone? What is critical Mach number? Any doubts here? Any doubts? Yes. Is this concept clear to you guys? Okay. All right. So you just have to remember that it is a free stream Mach number at which you first obtain the sonic flow. Okay. So now let's move on. Now I have a task for you. So let's take three different aerofoils. Okay. Let's take three different aerofoils. You can see there are three different aerofoils placed in free stream flow. Let's say the first aerofoil has the critical Mach number of MCR1, MCR2, and MCR3. Okay. Now these aerofoils are different in thickness, right? The first aerofoil is the thickest aerofoil, second is the thinnest, and the third one is less thicker than the first, but more thicker than the second. So can you arrange these aerofoils? Let's say this is 1, 2, and 3. Can you arrange them in the increasing order of critical Mach number? Can you arrange them in the increasing order of critical Mach number? So which has the lowest critical Mach number and which has the highest critical Mach number? It's very easy. Just think about the kind of flow it will have. How will the thickness affect the flow over the aerofoil? Yeah, those who are watching, can you do this? So 2, 3, 1. So you mean 2 has the least? Is it this? Or is it this? Sorry, I mean, yeah. Which one do you think is correct? Okay, so yeah, some of you guys have got it right, but not everyone. Okay, so let's see how thickness affects the critical Mach number for an aerofoil, right? So if I have a thick aerofoil, let's take a thick aerofoil and let's take a thin aerofoil. Okay, so I'll take these two. First one is a thick, this is thin aerofoil. So for same Mach number, for the same free stream Mach number, m infinity, what do you see? A thick aerofoil will suddenly expand the flow, will accelerate quickly, right? If it accelerates quickly, the acceleration is more, and the kind of Mach number you will reach on the surface is more, right? The local Mach number is more compared to the thin airfoil. Thin airfoil, because the curvature is less, the acceleration on the top surface is less, and the free stream Mach number, sorry, the local Mach number is less. So which should have the highest critical Mach number? Is it a thinnest aerofoil or thickest aerofoil? Which should have a highest critical Mach number? Is it thinnest or thickest? Yeah. Should it be thinnest aerofoil or thickest aerofoil? Yes, good, right. So yeah, Kanishka, you are right. Akash, you are right. Yeah. So highest critical Mach number is going to be for the thickest aerofoil. Sorry, lowest critical Mach number is going to be for the thickest aerofoil, because the acceleration is going to be sudden, and least is going to be for the thinnest. So the answer is 1, 3, and 2, right? So the thinnest will have the highest critical Mach number. Okay, so this has been a popular gate question. So yeah. Okay, so let's go to the next one. Okay, now similar to critical Mach number, we have a concept called as drag divergence Mach number, right? Now what happens here? So as I told you, if I take, let me take this aerofoil. If my free stream Mach number is more than critical Mach number, what happens? I generally have a supersonic pocket on the aerofoil where Mach number is greater than 1, and there's a sonic line, right? Now, if I further increase my Mach number, okay, if I further increase my Mach number, what happens is there will be a supersonic pocket, but the supersonic pocket will now terminate in a shock. Supersonic pocket will now terminate in a shock. Now, because of this shock, you have sudden reduction in velocity, because here it is Mach greater than 1 supersonic flow. Once you have a normal shock, the downstream flow is subsonic, right? So you have sudden reduction in velocity, which is abrupt. So you have a drag called as wave drag, right? There is wave drag coming into picture. So right when you have this shock, the drag is going to rise so much. Okay, the drag is going to rise so much. That is why we call this phenomena as drag divergence. And when this happens, the free stream Mach number is called as drag divergence Mach number, denoted by MDD. Okay, it is known as drag divergence Mach number. Okay, so you can see here, the CD is initially constant with Mach number, but after, so you have a critical Mach number, then suddenly slowly the drag starts to rise, because there is supersonic flow. And once the supersonic pocket is broken in shock, there is a normal shock standing on the aerofoil surface, you have a drag divergence Mach number. Right after that, the drag starts to shoot up suddenly. It starts to increase so much that close to Mach 1, the drag is maximum. Right? The drag is maximum. And then what happens? So, and then if I increase the Mach number above drag divergence Mach number, if my free stream Mach number is greater than drag divergence Mach number, then you see the supersonic pocket, the shock will move close to trailing edge. Okay, and after a point, you will see that the shock will exactly be at the trailing edge. Okay, that is when the drag slowly starts to reduce. Okay, so ideally, which is a very good condition for us. For us, we want the critical Mach number to be highest as possible, but we also don't want to approach drag divergence Mach number. So I want to be in this gap between critical and drag divergence Mach number. So how do I increase the gap? That is a question. That is a question, right? How do I increase the gap? For that, we have some ways to increase the critical Mach number or drag divergence Mach number. There are some very traditional ways. So the first way is to reduce the thickness, right? Make thin airfoils. So that is what we saw. Thin airfoils have highest critical Mach number. So if I make the aerofoil very thin, then naturally my critical Mach number will increase, right? So I have to reduce my T by C max to reduce the thickness. But if I consider this option, can I make the aerofoil as thin as possible? Can I make it very, very thin? Can I fit that into aircraft? Can I make wings of very, very thin airfoils? If I do that, what will happen? Of course, I will get a very high critical Mach number, but is that a good option? Yeah. Is that a good option? No. Why? What will happen if I make very thin airfoils? Yes. Yeah. So you will have structural effects, right? So it is not good for your structural strength, because if I use very thin airfoil, then this is your aircraft, there's a wing, right? So right at the wing root, the bending moment is so much, right? Because of the lift distribution, the kind of loads acting on your wing, it's a distributed load. So the bending moment at the root is so much, right? So if I make very thin airfoil which cannot sustain the high bending stress, then my wing will break, right? Structurally, my wing will not be held. So it is not really a good option to make very thin airfoils, right? So I cannot make very thin airfoils. I need to maintain a certain thickness. Okay. Yeah. So yeah, that is also a right option answer, because if I make very thin airfoil, I will not have enough space to store fuel, because generally sometimes in aircrafts there are also additional fuel tanks on wings apart from fuselage, right? So you need to store fuel. Okay. So that is why you cannot go to very thin airfoils. So what do? You can make wings which are swept back. You can give sweep to the wings. So if this is your aircraft, you can make wings which are swept back. Okay. So swept back wings means you give a span wise inclination to the wing with respect to the horizontal, right? So if you sweep the wing, what will happen? The effective Mach number that every aerofoil is going to see will get reduced, right? So this is the effective Mach number that every aerofoil will see. Although it is subjected to Mach number m infinity, but the effective Mach number that the aerofoil section will see will be reduced because of the sweep angle. Okay. So because of that, again, by the same argument, critical Mach number is increased. Okay. So these are two traditional ways of doing it. There is another way, which is a very interesting way to do, is to use supercritical aerofoil. So this is a very specially designed aerofoil which tends to play with critical Mach number and drag divergence Mach number. Okay, so we will see what exactly is this supercritical aerofoil and how does it help to increase your critical or drag divergence Mach number. Okay. So what is a supercritical airfoil? So if you see, the main function of supercritical aerofoil is to increase the gap between critical Mach number and drag divergence Mach number. So as I told you, between your critical and drag divergence is where I have the supersonic pocket, right? So that pocket is what I want without a shock. So I want to increase the gap between critical and the drag divergence Mach number. So this aerofoil is going to do that. Okay. So what do? They increase the drag divergence Mach number. Supercritical aerofoil is going to increase the drag divergence Mach number. Now, how does this aerofoil look? So this supercritical aerofoil generally looks like this. It has a relatively flat top. Okay, it has a flat top and it has a highly cambered trailing edge. Okay, it has a highly cambered trailing edge, and there's a reason why they have made it like that. And if you see this aerofoil, because of the flat top, when there is a flow, okay, when there is a flow, let's say m infinity is greater than m, because of the flat top, the expansion is not much, and there is a supersonic pocket for most of the upper surface. Okay, most of the upper surface. So of course there is a shock also. The supersonic pocket is going to end in a shock, but the shock is going to be very, very weak. So there is a weak shock. Because there is a weak shock, it will not increase your drag so much. Okay, it will not increase your drag so much. So in conventional airfoils, what will happen? This supersonic pocket will terminate in a very strong shock, which increases the gap, which increases the drag so much. Okay, so you can see here there's a comparison between the supercritical aerofoil and a NACA 6-digit airfoil. So generally NACA 6-digit aerofoils are also preferred. They are known as laminar flow aerofoils. They also have a very smooth surface which can sustain laminar flow for a longer distance. So they are also capable of increasing the drag divergence Mach number. But then the problem is here you have a strong shock. Okay, but critical Mach number, the supercritical aerofoil will have a weak shock. Okay, so supercritical aerofoil is always preferred. And if you see the conventional aircrafts which fly today, the kind of airfoils they use is closely resembling the supercritical airfoil. Okay, so the terminating shock is weaker. That is why it creates a less amount of drag. Okay, so some important things about supercritical airfoil: it has a weak shock wave, right? You can see this is the normal aerofoil has a critical Mach number over here. Supercritical aerofoil has it over here. So you see the drag divergence Mach number has increased by from 0.65 to almost 0.77, something like that, right? Which is a huge increase, right? This gap is huge. So now, why do you think supercritical aerofoil has a flat top, and why does it have a highly cambered trailing edge? So what happens is, because the top is flat, okay, because the top is flat and you have a curvature in the bottom, for 60% of the aerofoil, for 60% of the distance, there's a negative camber, right? You see there's a negative camber. Now, if I place this aerofoil in a negative camber, I'm going to lose my lift, right? Any aerofoil placed in a negative camber will lose the lift. So if I lose the lift here, I need to gain that lift, right? So to compensate that, in the remaining 30%, I will provide very high positive camber. Okay, I will provide extremely high positive camber. So because of that positive camber, the loss of lift which I had here is going to increase now. Okay, so there is loss of lift, but there is also increase in lift near the trailing edge side due to the extreme positive camber. So the total lift does not get affected by using supercritical aerofoil. So that is the advantage of using this kind of aerofoils. Okay, so that is what is written here. Okay, so I hope this was clear to you all. So we learned about the critical Mach number, we learned about drag divergence Mach number, and we learned about the ways to delay critical Mach number and the way to increase the drag divergence Mach number, and about the supercritical aerofoil. Okay, so can we now take some gate questions? So let's solve this question. So consider flow over a thin aerofoil at Mach number 0.5 at an angle of attack alpha. Using the Prandtl-Glovert rule for compressibility correction, the formula for lift coefficient can be written as dash. So it is telling you to use a thin aerofoil, which means you can use the results of a thin aerofoil theory. Okay, and this aerofoil is placed in a free stream Mach number 0.5. Okay, and it is kept at a angle of attack alpha. Okay, it is kept at angle of attack alpha. So this is m infinity 0.5. Okay, so we know because it is a thin aerofoil, it is a symmetric aerofoil. Okay, for symmetric aerofoil, the lift coefficient given by the thin airfoil theory is it is a naught into alpha, where a naught is equal to 2 pi. Right, so I can write CL is equal to 2 pi times alpha for a thin aerofoil theory, but thin aerofoil theory is based on incompressible assumptions. But here Mach number is 0.5, which is a compressible Mach number. So I need to use compressibility correction, right? So I use Prandtl-Glovert compressibility correction, which means this is my CL naught. So my CL becomes CL naught by root 1 minus m infinity square, right? Which is 2 pi alpha by root of 1 minus 0.5 square. Okay, so if you just try to solve this, can you solve this and let me know what do you get? Yeah. Can you calculate and let me know? Yes, you just have to substitute m infinity as 0.5. What is the answer? Option B, right. So the answer is 7.26 alpha. Okay. So I hope you understood this question. Let's move to the next one. So this is again a very interesting question. Let's see. For an inviscid compressible flow past a thin aerofoil, shown in the figure, free stream Mach number and pressure are denoted by m infinity and p infinity. The ratio of pressure at point A and infinity is 0.8, which means PA by P infinity is given to you as 0.8. Okay. Specific heat ratio is 1.4, gamma is 1.4. Mach number at point A is 1. So if Mach number at point A is 1, what is m infinity? What do I call my m infinity if Mach number at point A is 1? Yes, guys. What will I call my m infinity as? If the Mach number at point A is 1? Yes, very good. It is going to be the critical Mach number. Okay. So m infinity becomes the critical Mach number. So you have to find what is the value of this critical Mach number with the given data, right? So how do you solve it? You can assume the flow over this aerofoil to be isentropic in nature. Okay. The flow is isentropic. Because the flow is isentropic, you can write PA by P infinity as PA by P naught by P infinity by P naught, where P naught is a stagnation pressure which is constant for an isentropic flow. So this can be written as 1 plus gamma minus 1 by 2 ma square power minus gamma by gamma minus 1 by 1 plus gamma minus 1 by 2 m infinity square minus gamma by gamma minus 1. Now ma is equal to 1. So this can be simplified as 1 plus gamma minus 1 by 2. Okay. Is equal to PA by PA, P infinity, which is 0.8. So you know your gamma, which is 1.4. You can find out m infinity. Okay. How do I get this relation? This is from isentropic relation. So when you study your gas dynamics, you will learn about isentropic relations, which relates pressure and temperature at two different points in an isentropic process. So if you solve this, you will get m infinity. So I think you should get m infinity as 0.79. Okay. So the answer is 0.79. Are you all getting this? Did anyone try? Are you getting 0.79? Straightforward calculation, right? Okay, guys. So with that, we will end the session here. So that's all. We have learned about the compressibility effects. It was in brief. So yeah, in our lectures, we will dive more deeper into this. So yeah, that's all. Thank you, everyone. If you have any doubts, please ask. Any doubts? Okay.